Computer graphics as a discipline is all about placing pixels in sensible ways. Over the past 70 years it exists, we've discovered many ways of doing this efficiently. All this knowledge is now available to us as easy-to-use and freely available libraries, so we can use it without much thought. But I believe it's very important to have a good understanding of what's actually going on under the hood. That's why in this video I want to review one of the oldest and most important computer graphic algorithms, Bresenham's line algorithm. As the name suggests, this algorithm is used to draw lines, but I'll show you how it can be used beyond just that. This algorithm was developed by Dr. Elton Bresenham in the early 1960s while working at IBM's computational lab, and was formally published in 1965. And to this day, when you draw a line in your graphics software of choice, there's a good chance it still uses this algorithm, invented more than 60 years ago. The algorithm solves the problem of approximating a continuous line on a discrete grid. The task is not as trivial as it may seem, especially for 1960s computers that weren't very good with non-integer calculations. Bresenham's algorithm was originally designed to work with integers only. However, to build intuition, let's first approach this problem using floating point math. We can imagine every cell on the grid, or a pixel if you will, as a 1x1 square. The line starts and ends at integer coordinates on this grid. Now we need to decide which pixels along this line should be filled. Looking at this picture, it seems reasonable to assume that the best choice is the pixel whose origin is closest to the actual line. It turns out that this intuition is correct, and is in fact the basis of Bresenham's algorithm. In this example, the line is shallow, which means it spans more columns than rows. In this situation, we can walk through every column, find the closest row to the line and fill it. Otherwise, the line would be steep, and we would walk through rows, finding the column that is closest to the line. Let's focus on the shallow line example. To find the closest row to the actual line, we need to determine the vertical position where the line intersects the left side of each column. Dividing the number of rows the line spans by the number of columns tells us how much the line vertical position changes per column. This is what's called a line's slope. We know the exact vertical coordinate of the line at the start, and if we add the slope to it, we know where the line is on the second column. Adding the slope again gives us the vertical position on the third, and so on. Now that we know the exact vertical position of the line at each column, picking the closest row is actually trivial. We simply round the value. While this example demonstrates a general idea of how a line can be rasterized, we can actually do better. Remember that Bresenham's algorithm doesn't even require floating point operations to do the same, so let's move in this direction. And the first thing that we can eliminate is rounding. Notice that as we move from one column to the next along the line, the row either stays on the same level or snaps to the next. So instead of rounding the line position at each column, we can decide whether to move to the next row or stay on the same one. Making this decision is fairly straightforward. If the line crosses the midpoint of the row before reaching the next column, we move to the next row. If not, we stay on the same row. Adding the slope to the current line position gives us its vertical position at the next column. Calculating the difference between this value and the row's midpoint tells us whether the line has crossed it or not. We don't actually care about the exact value, only whether it's positive or not. If the line surpasses the midpoint, it will be positive, because the line's vertical position will be greater than the position of the middle of the row. If it does, we pick the next row, otherwise we stay on the same one. No more rounding, but there are more things to improve. Instead of tracking the exact line position at each step, we can track the difference between the line's vertical position and the row's midpoint itself. We can calculate the difference between the initial row midpoint and the line's next position right away. In fact, we can completely ignore the absolute row position and the line's initial vertical position in this equation. They are the same, so they won't contribute to the difference. On every step, we check if the difference is greater than 0. If it is, the midpoint will be crossed, so we need to move to the next row. Because of this, we subtract 1 from the difference, ensuring it now corresponds to the next row. If the value is below 0, the line does not cross the midpoint, so we remain on the same row. In any case, we add the slope to the difference to reflect the line's progression. And this is basically the idea behind Bresenham's algorithm, but we're still using floating point operations, so let's get rid of them. It turns out we can implement the same decision factor logic using only integer operations. We can eliminate the need for division by multiplying all terms by delta x, the denominator in our slope calculation. This changes the decision factor value, but not its sign, which is the only thing that matters for our decision making. We still have a fraction in our midpoint calculation, but we can eliminate it by scaling everything by 2. The sign remains unchanged, but now we avoid floating point operations entirely. This code, of course, only covers the shallow line with increasing slope case. To rasterize any possible line with this algorithm, the code must be able to handle negative slopes as well as steep lines with positive and negative slopes. There are various ways of doing it, see if you can come up with one. And now as promised, the application of this algorithm beyond just drawing lines. You know how in roguelike games you can only see parts of the map that are within your character's line of sight. Well, this effect can be achieved with the help of Bresenham's algorithm. Here's how it works. Pick a set of tiles around the player's character. For simplicity, it can be a square block with the character in the middle. For every tile in this set, start walking towards it from the character's tile, using Bresenham's algorithm. Reveal tiles along the way, stopping if the tile is opaque. As a result, all visited tiles are the ones within the player's character's line of sight. Notice that this requires quite a lot of iterations using the brute force approach, so consider ways of optimizing it when implementing in a real game. So that is Bresenham's algorithm. I hope you also see the beauty of this old algorithm. At the time of its invention, it was a big deal. So don't worry if it takes some time to wrap your head around it. It looks simple, but it took a brilliant computer scientist to come up with. It definitely took me some time to really understand how it works. And that's it for this video. Thank you for watching. Bye.